Hello everyone, my name is Saiful Islam. I am a PhD candidate at the University of Alberta, Canada. Today, I will present my study on a holistic design approach for innovative panelized light wood frame roof construction. The presentation will follow as background and motivation, new panelized roof system, case study analysis, connection test, and conclusion. Panelized construction is a form of off-site construction that has three steps: production, transportation, and on-site installation. Due to use of automation, this process is praised for its superior quality of construction as well as safe workplace. Typically, light frame panelized building production facilities have several workstations. For example, a local home manufacturer in Alberta has a wall framing station, floor production line, and roof production line. These production lines have some constraints. For example, for wall production line, the maximum framing height can be 3200 millimeter, and the minimum framing height is 1600 millimeter. Whereas for production line, for floor production line, this is 12,200 millimeter, and maximum framing length is 3200 millimeter. So if we want to produce any building component using these production lines, we have to consider these constraints. So current panelized roof production process is partially panelized due to the fabrication process of roof. The roof production process is same as stick build process. The only difference is it is being produced in the factory. The production process has several non-value added activities, and due to manual work, it is less productive compared to other workstations. As it can be seen into the figure, travel distance and the unit cost of transportation is proportional to each other. So for this type of roof production using the existing facilities, it is often required to produce 3 to 4 roof module for a single detached home. And due to high transportation cost, it becomes sometimes infeasible for long hauling distance. Also, in case of very complex roof production, offsite, it becomes impossible to produce roof offsite. In that case, the roof is produced on site, which increases the production project duration as well as product cost. Current roof production process requires 19 manual tasks, and it requires 90 man-hour. So in order to improve this production process, it is required to have a new roof system that can be produced in using automated and semi-automated workstations. The goal of this study is to produce a panelized roof using the existing automated semi-automated system and reduce the transportation cost. If we consider in case study a house that has a building footprint 10 meter by 6 meter with a gable roof 8 by 12, then the proposed new panelized roof system will have these elements. The system will have some ceiling frames. For this case study, it equates to 4 ceiling frames with different dimensions, 4 roof panels, 2 support wall, and some beam members spanning from one support wall to other support wall. It will also require very efficient connection system that can be used in the site to install. For this case study, The panel A width will be around 1.9 meter, whereas for the panel B it is 1.8 meter. To produce the ceiling frame, we need to understand the load path for the gravity load part. This figure shows the gravity load part for this system. As it can be seen in the figure, the complete gravity load from panel A is transferred to the support wall, whereas for this panel B, half of the half of the gravity load is transferred to the support wall, and half of the gravity load is transferred to the load bearing wall, making a 2-point loading on the ceiling frame. We change the location of this support wall and observe the corresponding deflection. It was revealed that span by 4 is the optimum location for this support wall that satisfies both production constraint as well as the service limited state. It should be noted that we intend to produce these roof panels using the wall production line. So the roof panels will be produced in the wall production line following the similar production process as walls, whereas ceiling frame can be produced using floor line or wall production line. The wall production line is a fully automated system, so it has a very high productivity, whereas the floor production line is semi-automated, so it has low productivity compared to the support wall. However, to produce ceiling frame using wall line, it is possible to produce the ceiling frame using LS cells, whereas the ceiling frame, whereas the floor production line can accommodate I-joist as well as LSL. Cost comparison of the both system producing ceiling frame in the wall line and the floor line shows that if we use wood I-joist to produce ceiling frame, the system becomes cost competitive with the existing system. In fact, the panelization of the roof will reduce the transportation cost, so it will be even more efficient and economic compared to the existing system. If we produce the ceiling frame using floor line, then for the case study, one ceiling frame will have dimension like this with the 3000 millimeter wide and 6000 millimeter span, and 4 ceiling frame will be required for this whole case study. The final layout will be like this. Next, the most critical part of this system is to have a very structurally efficient connection system that is easy to install and that will reduce the on-site workload as well. As it can be seen in this figure, it requires connection on the eave line. It also requires connection on the support wall with the panel A and support wall panel B, as well as it requires connection panel to panel connection, and it also required apex line connections. This figure shows the panel A to support wall connection. Basically, this connection is produced by using a screw, wood timber screw, that connects the top plate of the support wall to the panel A, whereas for the panel B, it is much more complex. First, the support wall has to be connected with a wedge piece like this, 140 by 200 millimeter, with 2 screws, and then the panel B is connected with an L bracket with the screws to the wedge pieces. The apex connection is also required in wedge pieces connecting like this, and a triangular beam is required at the apex that connects to the support wall with these screws, making a rigid joint. Panel to panel connection is basically using a screw, single screw. I'll talk about next about this connection more in this here. This figure shows the mechanism of this here. So as it can be seen here, one screw current goes from this wedge piece to the support wall start here. It should be noted that one screw is going to the start of the support wall and the other screw is going to the top plate of the support wall. And then using L bracket is connected with two screw to the support wall wedge pieces. And with these wedge pieces, one screw goes to the to here to connect this panel B, panel A. So since there is no connection systems exist, so we have to this tested following the ASTM procedure. We developed our own test setup. This A is the shared test of the screw with for the panel A to the support wall connection, whereas this one is the shared test of the wedge pieces with the support wall connection. And this is the simplified version of the angle bracket to the panel B connection. This C is basically window uplift test of this support wall A to support wall connection, support wall to panel A connection, and this is basically these two are basically panel to panel connection test, single screw, and this is the shared test for the apex line connection. The actual test setup looked like this. We investigated two types of screw. The first screw is manufactured by Orthoblas, which is HBS countershank screw, and other one is a timber screw, high-strength timber screw manufactured by Simpson Strong tie. The Orthoblas screw has a shank diameter 4.3 mm, whereas the Simpson Strong tie has 5.5 mm diameter for the screw shank diameter. This figure shows the test results for the apex. Getting the failure mode is very critical because we want to use some analytical models to predict the roof, predict the connection capacity. So for the orthoblast screw, it was observed that peak load was around 12 kilonewton, whereas for the Simpson Strong tie screw, it has around 22 kilonewton. So we use some European yield models, available European yield models for self-tapping screws to predict the load, and the result shows that those models predicts the connection capacity well. We tested only for the 8x12 flap. However, since these European yield models predicts well this capacity, so designers can use these models to predict the load for other type of roof. It should be noted that the shape of the wedge piece changes as with the slope of the roof. So this result shows that using the European model, it is possible to predict any type, load capacity of this connection for any other type of roof or any other slope of the roof. Also, these connections test gives us a load deflection curve of the connection. Using those data sets, we will be producing an complete finite element model of the roof, and thereby we will be investigating the load response of this system itself as a whole. And we plan to expand this type of roof system for other type roofs such as hoop roof. The limitation of this roof system is it cannot be used in case of commercial facility where large roof span, because it is limited for only residential construction. I would like to thank you, Aquabuilt, Simpson Strong Tie, and Orthoblast for their support. And now I will thank you everyone, and I will take questions now.